Hi, and hello to all of you. So welcome to my online electrical engineering and review tutorial channel. My name is Michael Pasis from Mapua University, and today we will discuss the generation of AC voltage. So from here we will also discuss the derivation of some of the important formulas, especially in terms of the sinusoidal current and sinusoidal voltage, which is E and I in small letters respectively. Okay, let us go to the principle itself. Consider that we have a coil and it is placed on a magnetic field, and then based from that there's a load on the other side, wherein the load is being attached from slip rings, and our coil was energized by a prime mover here. So a prime mover has a DC battery, and then from there it generates speed at a constant rate in a counterclockwise direction. Please take note that the magnetic field is from left to right, which is opposite on the speed or on the angular velocity. So angular velocity is 2 pi f. Okay, so when you say f, there is the frequency in cycle per second, but the unit of this is in radian per second for an angular velocity. Now if you use this, or you can apply it on a Cartesian plane, or apply it in this Cartesian plane. By the way, that is a rotating field type, which means that your main core is the rotating body, while your magnets is on a stator part. So it is a rotating armature type for smaller machine, because there is a rotating field type for larger machines, wherein the north and south, or the magnets, will be the one who will rotate instead of the coil. Now the north to south poles here is stationary. So for this, we project this here, and this is from left to right, and this is like this from north to south, and this is your coil. Okay, your coil has number of turns. Okay, one coil, you have 2 turns. Okay, from that, if you have this angular velocity omega, it will rotate rather in a counterclockwise direction. It will produce an instantaneous voltage E with respect to the magnetic field and also a magnetic flux. Okay, so we can have that equation as theta m cosine omega t. Now we have the y and x axis here. So the y axis is your E, your instantaneous voltage, while your x is your argument. We call this an argument, which is omega times t. Remember that omega here is in radian per second times time in seconds. That is omega times t, and then it will yield to a radian unit. Okay, without further ado, now your coil will turn in a counterclockwise direction, and it will produce a sinusoidal waveform. And please take note, if the coil is in parallel with the magnetic field, you will have a maximum E, or a peak-to-peak value maximum E, or EM in other words. While if that is in perpendicular, your coil is in perpendicular, okay, with the magnetic field, it will produce a 0 voltage. Or in other words, when we project this one, we can have this, your E versus your argument. And from here, you have, 3 points wherein your E is 0. Wherein E is 0 if the coil is in perpendicular with the magnetic field. And E is in terms of maximum, wherein this is the points where it is in maximum, EM positive and EM negative. Here, we could say this is E peak to peak value, where E is equal to EM if that is in parallel with the magnetic field. So you can project this one to here. And by the way, if this is in radian, we can have this in degree, respectively, in degree. So how you will do that? You multiply it by 180 all over pi radian, right? Okay, now in this case, if you convert it to degree, you have 0, you have 180 degree, and 360 degree. And if you consider the sine function, or 360 degree, okay, you will yield to a E of equal to 0, because you have 3 positions, okay, of your instantaneous voltage in terms of the 0 position. And you have a 90 degree, if you can see here, for a maximum position. Okay, hence, yeah, we have here a basic, okay, equation for the angle theta, that is omega t. Now, if you want to get the equation for instantaneous voltage E, you need to have the differential of the flux linkage, and the flux linkage is simply equal to this equation, N times Pm cosine omega t. Now, the N here, since you have N is one coil for this example, it will depend on how many turns that you have on your armature. So for that, we need to have that constant N to be multiplied. Okay, so for this, if you get the differential, okay, of that cosine, and we need to have the negative here to become an absolute value, then we have this equation, E is equal to Em sine omega t, and then you can apply it also on current. So current is Im sine omega t. Please take note that Em and Im are your magnitudes of your instantaneous voltage E and I. And this is in terms of smaller E and smaller I, which means that your voltage and current is with respect to time t. Okay, or simply with respect to your omega t or your angle theta. But in other words, it is with respect to your time, and hence you will have a sinusoidal waveform. Okay, we will discuss in the next slide, okay, RMS values and other formulas related to generation of AC voltages. Okay, let's move forward to the second part of the fundamentals. Now we have here some factors on how we arrive at an instantaneous E, and the factors based from the machine is the number of turns, the magnetic field or magnetic flux, and the speed of rotation, which is the omega or the angular velocity. And if we combine them in an equation, we have here this Em. Okay, that is the when say Em again is the magnitude or the maximum, okay, value of E, or the peak to peak value, and the F is the frequency in radian per second. Okay, now let's move forward to the so-called period. So since we already know that you have a sinusoidal and it will repeat, okay, depends on number of times, so we can say that the period is the time required to complete one cycle. So it means if you have, okay, this is one period, and then if you repeat it many times, you have N times T. So it means number of sinusoidal in terms of one period, you can get the whole signal. Okay, but anyway, no, you can compute for the period T by having the reciprocal of the frequency, and this will be in terms of seconds. One more thing that you need to know is the lagging and leading sinusoid. or lagging or leading scenario of a phasor. Rather sinusoid. Sinusoid is instantaneous, also called instantaneous value, because sinusoid is with respect to time t. So as you can see here, it depends on the time t here. If your omega here is 1, you will have time in seconds. So it with respect to time. Okay, so this is measured by using your oscilloscope. Okay, and if you have a sinusoid, how can you determine if the signal is leading or lagging? Okay, from the respective reference. You need to know what is the reference first before you can decide whether what is the signal that is leading or lagging. Okay, so I have some mnemonics here, so that you can we can simply analyze this. When you say first to show, so it means first to show, it is leading. Okay, and if last to show means lagging. And please take note, all of this is with respect to reference, with respect to a certain reference. Okay, how you will determine if the signal is reference? If it starts with 0. For example, this one. This is the sinusoid. The black one here is your instantaneous voltage, and it starts at 0. Okay? Now, the red and the blue signal here, as you can see on this in the whiteboard, the red here is first to show because it is first to show with respect to the black signal or reference. First to show this red signal. So hence, we have our main equation a while ago that to get the current, you have In sine omega t. Okay, but if you have an angle theta which is 0, for example, for E, the equation, this is either E or I, okay? So your E here will be automatically sine omega t because this one is 0. However, this one, you will determine if lagging or leading, it depends if first to show or last to show. If this is first to show, this is positive. The angle is positive. So it means this is positive alpha, not angle here. Okay, this is positive alpha. And since the blue here is last to show, this blue here, I could say beta, this blue here, okay, so it means last to show, it means lagging, and the angle is negative. So this is a negative one. So what will happen? You have your I here. I instantaneous is equal to Im sine omega t, but the angle is lagging and it is negative b or negative beta. So we will make use of this analysis on one of the problems on your on our main problems later. So we will have this application on one of the problems. So we will continue our basic principle for root mean square. Hello and good day to all of you. Now we will discuss the continuation of the generation of AC voltage, and we are on the root mean square value. Okay, the root mean square value is also has an acronym of RMS value of the signal. Okay, what is the root mean square or the RMS value of a certain signal? So this is the value of an AC given that of a DC signal when flowing to the same circuit at the same time will produce the same heat, okay, by the AC circuit with a given circuit as well and at the same time. So it means when you say heat, it means losses, okay, it is losses. So we can equate here the power at the DC and the power at the AC. Since they have the same circuit, as mentioned on the definition, they have the same resistance. So this is I squared R and I squared R. But the signal here is in DC and the signal here in AC. So whatever the value of the heat dissipated by the two circuits, you can get the root mean square value in terms of current or in terms of voltage, because in terms of voltage, you have V squared all over R. The R will cancel out. The voltage in terms of AC and DC will be the same, and you need to get that root mean square value. Okay, so it means that we need to have an equation here. So in terms of function, the root mean square of Rm is simply equal to the square root of 1 all over t from 0 to t ft squared dt. So again, you will have a hard time to memorize this, but there's a shortcut that I can share with you. Okay, for example, your signal is an AC circuit. Okay, so from 0, this is pi, then 2 pi, you have a full period of t here, okay, which is equal to 2 pi, for example. Okay, this is in terms of instantaneous current and voltage, and this is the argument, which is, I could say, omega t. Okay, the shortcut here is simply on the acronym of the root mean square. Okay, so when you say root means square root, okay, when you say mean is an average, right? So the average of this whole signal here from a certain period. So we could say period is twice t. So get the average from 1 over t from 0 to t of the function. Of course, you cannot integrate without dt. From 0 to t, the period, what we have discussed from the last slide. Okay, so ft is in terms of the function t, or in terms of time, and then root mean, that's the average. Remember, it's the average, and then you squared the signal. So that's why it is root mean squared. Now, it will depend on what type of function, because you can have an input signal of a square wave, a triangular wave, semicircular wave, the pulsating DC, etc. So there are many types of functions, but we will concentrate more on AC signal, a sinusoidal signal, for the for example, derivation. However, if the signal becomes like this, a triangular wave, the root mean square value will be different, and you need to derive it. Okay, now let's concentrate on the sinusoidal signal, and let's review the trigonometric identity of sine. So sine squared theta, or in terms of the property of the squared of the sine, is equal to 1 minus cosine 2 theta all over 2. We need to do this because we need to integrate the squared of a sine. So to become integrable, we need to have this property or identity. Okay, we need to apply the formula of the root mean square in a sinusoidal signal. And if you can still recall, okay, the f of t, or the function of the signal, okay, in terms of instantaneous voltage and current. So you can still recall this one, okay, from our previous slide, that is Em sine omega t. But omega t can be theta. So instead of omega t, you can have theta here, the argument. So you can substitute that function here and d theta. Then you squared, and then from 0 to t, the whole function, the whole period of the sinusoidal signal here, which is t. So what will happen is you 1 all over 2 pi integral of 0, from the limit 0 to 2 pi, and then Em sine theta squared d theta. Now, to have this integrable, you need to go to the identity of the sine squared. So what will happen is you can have 1 minus cosine 2 theta here, and then you can have the constants. Okay, here at the left side of the integral. So you have em squared all over 4 pi from 0 to pi, and then you can now integrate this one. You can now integrate this. Okay, just do the math and integral calculus. What is important here is this equations here. It can be current or voltage. That in a sinusoidal signal, the root mean square value is equal to ERMS is Emax all over square root of 2. Emax is the peak-to-peak value, or IRMS, or the root mean square of the current, is equal to Imax all over square root of 2. Now, these root mean square values are the values that is you see on your meters, like your voltmeters. Okay, the value of the current and the voltage there is represented by a root mean square. And you already know what is root mean square about. Root mean square again is the value of an AC signal that is equal to the DC signal that will produce the same heat dissipated on the same circuit at the same time. Now, we can now go forward to the other fundamentals. Okay, let's continue our discussion on the generation of AC signal. So for this, we already described the root mean square value of a signal. How about if you want to get the average value of the signal? We already described what is average value in terms of a period t. Now, this is also the same thing. When you say average, this is the average value of a certain signal. The only lacking if you want to become RMS is the square root and then square root of the signal. So, chipips, kapatid, this is the same thing, that the signal average or F average is simply 1 all over T of the period integral from 0 to T, Ft dt. Okay, now, you need to apply the sinusoidal signal in in getting the average. So, we'll do the same pattern a while ago, but the only difference is the time, signal, rather the period T. Okay. I'll draw again a sinusoidal signal from 0, pi, and 2 pi. And you have the whole period t. However, if I use the whole signal here, okay, which is 2 pi, the answer will be definitely 0 in the average. Simply because, as you can see from the signal itself, this is the positive peak and the negative peak. They will only cancel out. So, the average here is matic 0. Okay, by common sense. So instead that having a value of 0, you just get the half of the signal so that you can get the average. So instead of 2 pi, I use pi as our period. Okay, from there, we'll do the same pattern. Okay, the theta here is omega t from our previous slides, and d phi so that you can integrate. Okay, now this is already integrable. So, by integrating sign, that is negative cosine from 0 to pi, evaluate limits, and we can have this value here. Okay, so 2 over 5 is 0.637 of the maximum value. This is the same thing if you use I average. So, this will become I max 0.637. Now, there's a numerical value as well of in the root mean square. You can still recall that your ERMS is simply equal to whatever the maximum value divided by square root of 2. 1 all over square root of 2 is also 0.707 of the maximum value. So it means in terms of numerical value, 0.707, 1 over square root of 2, but in terms of average, 2 all over pi. And please take note, this is only for a sinusoidal signal. Okay, there are some definitions that will become very handy when finding an average value given an RMS, or getting the average value getting the average value given Emax, or vice versa. We will have that kind of problem later, but these are some definitions which is very handy on generation of AC circuit. The form factor FF. Okay, the formula is root mean square value of a signal divided by average. Now, this form factor is only for a sinusoidal signal. But if the signal becomes different, the average and the RMS values will be different as well. So, you will have a different value. Now, this is unitless. So, the root mean square value of your form factor if you can still recall, is EM all over square root of 2, or simply, we already have this one, 0.707 EM. And the average here, we have in terms of the maximum value, you divide it by 0.637 of EM. Yes, this is the one. You can cancel EM here. The answer is 1.11. Now, there is also one definition, which is crest factor maximum all over RMS. So, therefore, to get the maximum value here, just multiply square root of 2 times ERMS, and then the ERMS value will cancel out. The answer is square root of 2. And please take note, this is only for sinusoidal signal. If the signal becomes different, you need to recompute RMS and average. The crest factor and the form factor will be different as well and unitless. Now, we can solve problems on AC generation. See you.